So, all right, guys, it's about showtime here. Thanks for coming over here today. We got some more people making their way in. Um, welcome to another review. It's good to see what a turnout. I would have been doing this for all of the midterm. I just assumed nobody would come. Both nights, a lot of people showing up, so I am stoked about that. Let's see, just quick overview here. I'm gonna do this review for a couple hours, then I'm gonna just go hike down to my office and hang out down there until midnight. So anybody who wants to do any post-review additional studying or ask any further deeper questions or anything like that, you can certainly do that. So I'll just be downstairs pretty much all night after the review is over as well. I'm a night owl, so this is perfect for me. In the morning, not so much. I'll try to get here a little bit early. My first class is at 10. Hopefully I'll be up in the office by 9, maybe 8:30 or so. I'll shoot for 8:30 probably. But we'll see how much sleep I get. I didn't get much sleep last night, so I'm kind of struggling here a little bit. I'm also going to send this video. I'm currently taking a video of this session. If you need to leave early, or even if you stay for the whole thing, but you just want to review something again, I'll have that out to you right after the review tonight. Last night I did a review that took almost 3 hours. I did send that out through an email. So if you missed last night's review or want to review that again, you can do that. My plan here is to try to hit some of the things that I didn't go over last night quite as thoroughly first, and then cycle back to some of the stuff that I've already gone over, but maybe with some slightly different problems. So it's not totally just a repeat of exactly what we did yesterday. So I think I'm gonna maybe approach it that way. And it's just totally casual. So if you have questions, I have no agenda, I have no timeline. I'm really open to anything you guys want to ask me about. If you have any concerns or you just want me to explain something again, don't hesitate. This is not the time to be shy. Just feel free to throw out any thoughts that you have. Now, in last night's review, I spent the first half hour kind of just going over all of the material. I just did a quick little drive-by of everything that was kind of in those 4 chapters. I think I'll skip that tonight. So if you want to see just a sort of 30-minute overview where I sort of hit the highlights, just talking through them, maybe take a look at the video that I sent out last night from yesterday's review. For tonight, what I think I'm going to do is just remind you again about the sections that are going to be on the test, but without going into all the details, because I want to get right into the problems tonight. These are the 4 chapters, right? And everybody has been commenting, and you're all correct that there's a lot of material here. I do really feel strongly, though, that by working hard to get this material down, you are actually getting yourself very well prepared for this comprehensive final exam that's going to be just another week from now. So you're kind of getting 2 for the price of 1 in terms of your studying effort. So thank you for your hard work this week. I think it will pay off next week, at least I hope it will. Each of these chapters, roughly a quarter of the exam. And keep in mind that although chapter 7, it only says a quarter of the exam, we need that chapter 7 material to do a lot of the stuff in chapter 9 as well. So it's a really important thing, the eigenvalue, eigenvector theory here. Really important. Got to be able to find eigenvalues and eigenvectors. Deal with defective and non-defective systems, things like that. So make sure that you're solid on that. And then chapter 6 is the older material on kernel and range. I'm probably going to start with a little bit of that earlier in the reviews. Last night I didn't do it till the very end. So tonight I'll probably try to hit a little bit earlier. Chapter 8, we did this really thoroughly last night. I did group work number 14 with everybody. So that's in that video early on in the review last night. So I would maybe do a little less on this tonight, or at least I'll push it off towards later in the review, just to kind of mix things up a little bit. But yeah, honestly, if you look hard enough and thoroughly enough, you will find material and examples about everything. I mean, I'm not trying to hide anything from you. I'm basically just laying it all out there. I haven't written the test yet. I have no idea when I'm going to write it, but sometime between now and tomorrow morning. But at this point, I am just totally in the mood to just like share absolutely everything I can. That's always my attitude about these things. So does anybody have any questions before we jump in? Okay, remember, I will be giving you a table of annihilators and a table of integrals. If you try those sample midterms, or if you at least try one of them, you'll see that I have that table right there in the front of the exam. It's exactly how I'm going to do it for you guys as well. So it'll be already prepared for you. Yeah, so that will be given to you. Other than that, yeah, no calculators, no notes, no books, nothing else should be needed, hopefully. We'll be good to go without all of that. So anyway, I think what I'm gonna do is jump into some practice problems. That sound okay? So let's start off, and I'm gonna kind of go in a random order here because on the exam, you might find yourself doing it in that way as well. So I found a problem in the book actually that I want to do, which is in the review section here in chapter 9. So I'd like to solve x prime equals a times x, where capital A is the following matrix: -7, -6, -7, and then -3, -3, -3, and then 7, and then 6, and then 7. And before I go any further, does everybody recognize, is this chapter 6? Is it 7? Is it 8? Or is it 9?
9.
No, it's chapter 9, right? We see that this is the whole ball game in chapter 9, right? Is solving that system, x prime equals ax. So in this case, we have a linear system of differential equations. This is what we would like to solve. Now, what you might notice about it right away, what is usually the first step in solving a linear system like this that we would have to do? Lynn?
We put the lambdas on the diagonal.
Okay, so we're trying to find the
eigenvalues.
eigenvalues, right? The first thing is to try to find the eigenvalues. Now, the first thing I notice about this matrix is it doesn't have any zeros in it at all. It doesn't look very favorable to cofactor expand anything. So how about we give a hint here? And I would actually give you this hint. If I was going to ask this question on the test, if I decided this was on the exam, I would give you this hint. And the hint that I'm going to give you here, guys, is that A is not invertible. A is not invertible. So we have a matrix that's not invertible. I wonder how that might help us. Because, yeah, you know, in this case, doing the cofactor expansion of A minus lambda I to solve for the lambdas is not going to be very nice. It's just going to be pretty tedious. There's no nice numbers here in this matrix. Nathan?
Would that mean that the determinant of A is not, or it's 0?
Okay, the determinant of the matrix is 0. This is a good point. And are you going somewhere with that thought?
Yeah, well, it's a 3 by 3, so wouldn't it have to be 3 zeros for lambda?
Well, check your fun facts on that. Don't forget that when you add up your lambdas, they should add up to whatever the diagonal adds up to. So in this case, -7 plus -3 plus 7 is -3. So my 3 lambdas should add up to -3. Eduardo?
That result in a row of zeros?
Yes, and we can even see it actually, can't we? Notice the first row and the third row? They're just negatives of each other. So if we did an ERO here, we could zero out the bottom row. That's compatible with saying that A is not invertible. I want to go back to what Nathan said though. The determinant of this matrix will be 0. Do we know anything about determinants related to eigenvalues? Evan? Exactly. We have 2 fun facts that I really want everybody to know. If I add up my lambdas, right? So maybe I'll just put this here. If I add up my 3 lambdas, they should add up to the trace of the matrix. Okay? And in this case, the trace of this matrix, if you add the main diagonal, -7 plus -3 plus 7, this would be -3. So my lambdas should add up to -3. But the other fun fact, which Evan just pointed out, is that when I multiply the lambdas, I should get the determinant of the matrix. And that actually tells me maybe even more helpful information than I realized. What can we tell so far just from using these fun facts? Is there anything about any of the lambdas that we would now be able to say? Yeah.
One of the lambdas has to be 0.
One of the lambdas has to be 0, right? You're multiplying these three numbers together and you're getting 0. So one of them has to be 0. Obviously they're not all three going to be 0, right? But there will be a 0 here somewhere. So at some point there is a 0 eigenvalue. So even without doing the characteristic equation, right? We can figure this out from this fun fact right here. The product of those eigenvalues is 0. Now, there's two other lambdas, and for the other two lambdas, this fun fact isn't gonna get me any further than I've already gotten, because I've really got 0 equals 0 now. And this fun fact, well, one of my lambdas is 0, but the other two of them then would have to add up to -3, but that could be lots of possibilities, right? It's not clear to me how to make that happen. So here's what I'm gonna recommend. I'm gonna recommend that we just go for this lambda here first, just see what we can get out of it, and then kind of take it from there, okay? So I'm gonna go ahead and do that. I'm gonna look at the null space. So we don't know what all of the other lambdas are yet, but we at least have this first one in our hands. And so let's see what we can figure out as far as the eigenvectors goes, right? Because what I'm doing right now, guys, is trying to find the eigenvalue eigenvector pairs. So, well, in this case, I just take the matrix A and I do nothing to it, right? I basically just leave it as is. So -7, -6, -7, and then -3, -3, -3, and then 7, 6, 7. We just basically are finding the null space of A itself. This matrix, remember, we have to be able to cross off a row because this is never invertible. And I'll just cross off the bottom row. It's literally a multiple of the first row. And so now what I can see is that, well, I'm not gonna be able to cross off any more than that. These other two rows are not multiples. See, sometimes you can cross off 2 rows. Here you cannot do that, right? So you have to live with the 2 rows that you have there. Let's just go ahead and put the row of -3s up on the top, but let's change it to 1, 1, 1. So I'm gonna multiply the middle row by -1/3, and then move it to the top. We'll leave the top row in the middle here for the moment. And I'm gonna do one more ERO, so 1, 1, 1. And I'm gonna take the first row times 7 and add it to the second row. So if I take the first row times 7 and add it to the second row, I should get 0, 1, 0. So it's actually not so bad. You get something looking like this. So there is your eigenvalue, lambda equals 1. Lambda equals 0, giving me this setup here. And we have our x, y, and z. And so I have a free variable here. The free variable is going to be z equals t. Okay, so z is free. There's no pivot on z. But the y variable is equal to 0, right? So 1 times y has to cancel out to 0. That just means that y itself is 0. And then from the first equation, x plus y plus z has to add up to 0. So in order for that to happen, the x would have to be a -t. So that all 3 variables add up to 0. And from that, I can now find my eigenvector. And my eigenvector here is going to be -1, 0, 1, right? So we're busting out the variables on that. Okay, so we bust out those variables and that's what we would have. So far, so good. And I'm able to make one solution right now, which would be x1 of t, which would be e to the 0t, that's just 1, times this eigenvector. So -1, 0, and 1. Right, everybody familiar with that? Everybody remember that? The solutions are gonna all be based on those eigenpairs. So x of t would be e to the lambda t times v. At this moment, the lambda is 0. And so e to the 0 goes away, and I just get the eigenvector, which we just derived right here. So this is going to be one of the 3 solutions. Remember, we have to have 3 solutions to this system in order to be able to write down the full-blown general solution here. Right. Okay, so We have one eigenvalue, which is 0, and we found one solution that corresponds to it. But we have two more solutions to go. Is everybody with me so far? So this isn't quite working out the way I had thought it was going to. I'm winging this because I just found this problem in the book right before the review and thought it would be a good one to do. And it is a good one to do. But the thing that's a little tricky here is what about the other eigenvalues? It turns out in this case that I probably would need to give you another one of the lambdas, maybe as part of the hint. Let's go back. A is not invertible, and I'm going to give you a little more of a hint here. So let's just say, and lambda equals -3 is an eigenvalue. Probably not obvious that that's the case, but it does turn out to be the case. So I'm going to make the problem a little easier by giving us this hint. And I might do that to you. I might give you maybe a hint where I give you some of the lambdas, but not all of them, right? So in this case, if I gave you that -3 was an eigenvalue, then, well, at that point, if we have lambda equals -3 as an eigenvalue being given to us, now you can see that we have a 0, we have a -3, and so what's the other eigenvalue going to be? Also 0, right? Oh, so actually 0 is going to be an eigenvalue twice, but only produced one eigenvector. What's that tell you about the matrix A?
It's defective.
Defective, right? The eigenvalue 0 does not pull its weight, right? So this is going to be defective with lambda equals 0, 0, and -3. Which defective case is it? What would we call this defective case? Evan? Mixed eigenvalue defective. So in the review session last night, I did a super defective example. So I thought tonight maybe I'll do a mixed eigenvalue example instead. This is mixed eigenvalue defective right here. Okay. So let me come back to the eigenvalue 0 in a minute. I'm going to look at this other eigenvalue first and just see what I can figure out from that, and then we'll go back to the first eigenvalue to get another solution. For lambda equals -3, of course, we're going to have to do another null space here, right? So I'm going to add 3 to the main diagonal of the original matrix. So I'm going back to the original matrix, and we very carefully add 3 to everything. Guys, all it takes is one little sign error, one little miscopying of the matrix, and you can throw this whole thing out on whack. So you really want to be cautious with this, because that doesn't really relate to how well you know the material. It's just like, yeah, if you make a little mistake, it can just really make the calculations hard to do. So just try to be careful, do the best you can. Nobody's perfect, but just do the best we can here. I'm going to add 3 to the main diagonal there, and I also have to do that on the bottom row. So 7, 6, and 10. Okay. And what I have to do now is assume, as usual, that this matrix is not invertible, which means I must be able to cross off a row. And a lot of times it doesn't matter which row you cross off. I usually like to cross off a row that I don't want to have to think about. A row that looks like bad numbers, messy numbers. Is there a row that you guys don't like here? Yeah. Maybe the bottom row. Okay, that sounds good. I would probably keep the middle row. The middle row has slightly nicer numbers in it, because I can just divide by -3 here and get some pretty nice numbers. So in fact, let's go ahead and divide the middle row by -3 and move it to the top. And then I'm going to recopy the first row in the second row. And then I'm going to add 4 times the first row to the second row in order to get a pivot in this second row where I want it. And I'll get 0 and -6 and -3. So here's my pivot here. Here's my pivot here, like so. All right, so that's so far so good, I think. Yeah. This row is not going to be important at all. And again, we have Z being free. So the x, y, z, like usual, we set up the z as a free variable. If I now want to solve for y, I just have to figure it out from the second row here. Negative 6y minus 3z, that's supposed to add up to 0. So if I want to solve it for y, what is that? Negative 1/2 of t. The y value, negative 1/2 of z. If I solve for y, I think I've got that right. Negative 1/2 of whatever z was. So that's negative 1/2 of t. And then I have to figure out what x is by using the first row. The first row just says x plus z. X plus z is 0. So x plus z is 0. And so the x is just the negative of whatever z was. That's just negative t. All right. And I'm going to go ahead and bust out the t on that and get my vector. So my eigenvector is negative 1, negative 1/2, and 1. Quick reminder that you can always multiply a correct eigenvector by a scalar multiple, and it'll just give you another correct eigenvector. So if you don't like fractions, you could double this vector and take that just as well. It makes no difference. I'm going to leave it the way it is. There's really no harm in doing that. But the point being now, guys, that I have my second solution here. You know what? I'm actually going to call it my third solution. It wouldn't be wrong to call it the second solution, but I want to put the two solutions involving lambda equals 0 together. So let's just call this the third one so we don't get confused. E to the negative 3t times the vector negative 1, negative 1/2, and 1. There is the third solution to our system. And so what remains for us to go back to now is I need to go back to lambda equals 0 again, because there is another repeat of lambda equals 0. This is an effective system, and I have to come up now with a second solution that corresponds to 0. And this is where we do the stuff we just learned this past week with the W's, right? Everybody remember this? So the way the x2 of t is going to look is it's going to be e to the lambda t times w1 plus t times w2. Okay. And yeah, hopefully you guys are getting a little bit more comfortable with this now that you've at least done the homework on this section. There's this diagram that I've been trying to sell to you guys. I hope that you're enjoying it reasonably well, where you start with W1, you're going to hop along the arc of this diagram, and that's going to leave you with W2. And then you're going to hop one more time across this diagram, and you had better end up at 0. So we are going to I'm just refreshing your memory here how this works from just a couple of days ago. We're going to choose W1 in such a way that this diagram works. Okay. There is a diagram that has a W3, 4, and 5 in it, but remember that one only comes up if you're in the super defective situation. So again, last night I did one of those where you have to use the bigger diagram. Here we only need this much of the diagram, which sounds like a nice thing, but actually this case in my mind is sometimes a little bit harder than the super defective case. I'm going to show you why in just a second. Right now the lambda is 0, so e to the 0 is just going to cancel out the 1, and it's really just going to come down to figuring out the w's. So W1 needs to survive a minus lambda I. Remember, lambda is 0. So W1 needs to survive A, but not survive 2 powers of A. That's it. So we've got A already in the problem. We just need to square that matrix. So one thing we have to do here, guys, is we do have to calculate A squared. So I'm going to practice my matrix multiplication. So here's our matrix. We're going to write it down 2 times right next to each other. Just copy it again. -7, -6, -7, -3, -3, -3, and then 7, 6, 7. So I actually have to multiply this out, and unfortunately I did not do it before the review. So this time I'm actually going to have to do it. figure this out. So make sure, guys, that you can do matrix multiplication of something like this, okay? The numbers are gonna be, yeah, we'll see. So I go across the rows of the first matrix and down the columns of the second matrix. So in the upper left corner, I'm just doing a dot product of the first row with the first column. So that's going to be 49 plus 18 minus 49. So that comes out to just 18, right? And then when I go to the top middle entry, I do a dot product of the first row with the second column. 42 plus 18 minus 42. Net result of 18 again, okay? Top right corner, what do I have there? 49 plus 18 minus 49. That comes out to 18 as well, okay? And then I go to the second row and I do the same thing. So 21 plus 9 minus 21. So 9. Middle entry is 18 plus 9 minus 18. That's also 9. And then 21 plus 9 minus 21, that's 9. And now we go to the bottom row and we have negative 49 minus 18 plus 49, and that's negative 18. And I can pretty much guarantee you that this bottom row is just going to be a bunch of negative 18. Ooh, I'm kind of glad that this came out like this. I'm glad that it came out like this, because I'm going to show you why I think this is the hardest of the three cases. It's because I have to choose W1 so that it will survive this matrix when I set it down as a column next to it, but it should not survive this matrix. And the trouble here, guys, is that the matrix, or sorry, the vector 1, 0, 0, that won't give you the first column here. It will survive. 0, 1, 0 will also survive. It'll just give me the middle column. And 0, 0, 1 will also survive because it'll give you the third column. This matrix does not have any column that is just all zeros. So that I cannot choose W1 like I did in class and like I did in the super defective cases. I can't just choose W1 to be 1, 0, 0 or 0, 1, 0 or 0, 0, 1. None of those will work. I have to be a little more clever here, guys. I need to come up with something here that will end up canceling out completely. That's going to be the trick. And there's lots of right answers. Don't get me wrong. There's lots of right answers, but we can't just fill up a standard basis vector here. We have to do something a little more clever than that. Does anybody want to try it? Oh, David.
1, negative 1, 0.
Let's check that one out. I like it. I like it. So if I do this dot product now, 18 minus 18 plus 0. 9 minus 9 plus 0. Negative 18 plus 18 plus 0. It works. It gives me 0, 0, and 0 all 3 times. So if we propose that as our W1, and by the way, I saw other hands up, there could have been other answers that would have worked as well. But if we propose that as W1, it will not survive 2 powers of A. That's good. And it's supposed to end up at 0 eventually. Does it at least survive 1 power of A? Because it does need to survive long enough to produce W2. Let's check it out. If I put, this is the original A right here. If I put the vector that David proposed, which was 1, negative 1, and 0 right here, and I do this matrix multiplication, let's see what W2 would be. So W1, I'm going to recopy it right here. We pick 1, negative 1, and 0, which I think is an awesome choice. And now we're going to try to see what W2 is. For W2, we use A minus lambda I applied to W1. Here's W1, and here's A minus lambda I. So let's just do this matrix multiplication, guys. Negative 7 plus 6 plus 0. That comes out to negative 1. That's the top slot. Awesome. It's not going to be 0, 0, 0. Okay, what about the middle entry here? Negative 3 plus 3 plus 0. That cancels out to 0. And what about the bottom slot? 7 minus 6 plus 0. 7 minus 6 plus 0, that is a 1. There we go. Oh, and by the way, just happens to be the eigenvector that we had come up with before. That should be not surprising. Remember that this W2 does not have to be the same eigenvector that we got before. Here it just happens to be. But if David had given me the vector 10, -10, 0, then we would have gotten -10, 0, and 10 here, and it would have been a multiple of the original eigenvector, and that would have been fine. Okay, so guys, using this, I can write down x2. The x2 of t. Again, remember the e to the lambda t is just 0 here. So we just go straight into writing down w1, which is 1, -1, 0, plus t times w2, which is -1, 0, and 1. You can just put a circle around that, so we can find it easily enough. I probably should have put a circle around my x1 as well. Because if you've done a good job of, keeping track of all 3 of your solutions here, then for your final answer, which is what we're ready for now, says to solve this system. So for your final answer, you can just go ahead and write x of t equals c1 times x1 of t plus c2 times x2 of t plus c3 times x3 of t. Okay, so there you go. That would be okay to just leave it as that. Assuming I can find x1, x2, and x3 easily enough. Okay, so this is a mixed eigenvalue case, and it's actually a mixed eigenvalue case where your W1, you actually had to think about it a little bit, right? You had to pick some vector here that would get killed by this matrix. And none of the standard basis vectors would work. We have to be a little more careful with that. Do people follow this? Is it okay? Do we want any clarification on that? Yeah, Tony?
So for finding W1, you have to make up a column or whatever.
Yeah, I gotta make this column in such a way that when I do these dot products, remember, you're gonna go across the rows here and down this column. In such a way that when I do those dot products, I get 0, 0, and 0 every single time. Yeah, and that's the part that takes just a little bit of creativity. Yeah. I mean, you could really, if you wanted to, you could set it up as an equation. You could just put A, B, C here. Let's say you didn't want to just wing it. If you didn't want to just wing it, you could put A, B, and C here and then just literally write out the equations. You'll get 18A plus 18 plus 18B plus 18C equals 0. And then from there, you can finagle a choice of A, B, and C that works. Yeah, so that's also totally fine. Look at this, somebody wrote, please do not use disinfectant wipes on the whiteboard. Somebody must be messing up this room too, because that was why my board wasn't erasing last week in that other room. I think it's been a problem, not just in that room, but in a lot of these rooms. So, okay.
Is it possible that we get an initial condition, an initial value?
Yeah, if I had given you an initial value like x of 0, then you would do everything the same as what I've just done here, and you would get 90% of the credit pretty much. The last part would just be, okay, now that I have this final answer, I have to plug in 0 for t and set it equal to whatever was given as the initial value. And that would be allowing you then to solve for C1, C2, and C3. Okay, so that game plan has been going on ever since chapter 1. If you have an initial value, then you can solve for the constants that are in the general solution. Yeah, so that's the idea there. Okay, other questions here? Good so far? Okay. Yeah, so I feel good. We did a nice example here of a defective linear system. Let me talk about the kernel and the range a little bit, because that one did not get covered as much last night. So let's make a problem up that we can work with here. Try my best to cover everything again. Okay, so let's try number 2 here. Okay, so I'm going to define T to go from, let's go from P2 of R to what I'm going to call W. W is going to be the set of 4x4 skew symmetric matrices. And then via, so I'm going to do this. So T of, I have to plug in a quadratic polynomial, something that looks like ax squared plus bx plus c. And I have to spit out a 4x4 skew symmetric matrix. Okay, so I'm going to create the formula here. Right, so I don't know how well you guys remember skew symmetric. These are the matrices that have zeros on the main diagonal. They have to have zeros going like this. And then on the upper triangle, you just have the negatives of the lower triangle. So let's just say I'm going to do A plus B, and B plus C. So that means in the first column, I would have negative A minus B, and negative B minus C. That would just be in the first column. And then maybe in the second row, I have a 0 and a 3B. So that means in the second column, I would have a 0 and a negative 3B. And then maybe I would have in the 3, 4 entry, let's just go ahead and use 4A plus C. So then in the 4, 3 entry, I have to have negative 4A minus C. Looks a little weird, but this is a skew symmetric matrix. The numbers that are above the main diagonal will always just be the negatives of whatever is below the main diagonal. So I just want to make sure that the question is reasonable. The output here has to be in W. The input has to be in V. Adam?
Would we be setting up that equation on the exam?
No, everything that's on this board so far would have to be given to you. Right, exactly. It would be given to you, and then I'm going to ask my question. So the question is just going to be to find bases for the kernel of T and the range of T. So find bases for the kernel and the range, and decide if T is 1-to-1 onto both or neither. So this kind of hits a lot of chapter 6 just in one big question here. Okay, so it's a quick way to cover a lot of ground. By the way, guys, I'm making a relatively hard example. One thing I don't ever want to be, I always in my review sessions, whenever I used to do these, and maybe I'm starting them up again now that I'm having such a good turnout, but I always tried to make sure I wasn't just doing all the easy problems in the review session and then everybody's going to the exam like, oh my God, this is like 10 times harder than the review. So I'm really trying to not make these problems too easy. This is pretty, messy, to be honest with you, to ask you to play around with something like that. But, I think we can handle it in the context of the review session. Okay, so we're going to try. Let's see. So the first part is asking us to find bases for the kernel and for the range. Where do you guys want to start? Do you prefer to start with the kernel or do you prefer to start with the range? Kernel? Okay, we can start with the kernel. So for the solution then, if I'm going to start with the kernel, can somebody remind me, how do I find the kernel of a linear transformation? David?
Basically, make them equal 0.
Okay, same thing that the person last night said. So that is not really wrong, but I just want to point out that the kernel of T being equal to the null space is only strictly correct if we're talking about a transformation from Rn to Rm where there's a matrix in advance, right? So there has to be, like, you have to already have an M by N matrix here. And in that case, the kernel of this kind of transformation is always just the null space of A, and the range is always the column space of A. A very good thing to know, for sure. I could ask you this type of a transformation. It's a very common one. But in this problem, of course, my V and my W are not Rn and Rm. They are these different vector spaces, whatever. So because of that, there really isn't a matrix here. Now, I know some of you are looking at me like, wait a minute, this is a matrix. This is an object in the output vector space W. That's different than saying that I'm using a matrix to actually do the transformation, to actually make it run from Rn to Rm. So this is a matrix transformation. The matrix here is not a vector. This matrix is actually the thing that's running the transformation over here, right? In this problem, yeah, there's a matrix here, but honestly, it's just a dead object. It's not part of what's creating the movement of vectors from V to W, right? It doesn't do that. So I'm going to hesitate to call the kernel of T the null space of the matrix here, because there really isn't a matrix running the show right now. So do we have a more general way of thinking about what the kernel of T is, ma'am?
We're going to want to set T of ax squared plus bx plus c equal to 0.
That's it, right? So the more general sort of always applicable definition is that you take your transformation, right? T of ax squared plus bx plus c, and you set that equal to 0. Now, when I say set it equal to 0, I don't mean the number 0. I mean set it equal to the 0 vector of W, right? The output of this transformation. And the output should be a 4x4 matrix, the 0 vector of which is just the matrix of all zeros. So technically, this is the way we would be starting this off. Okay, so it's not the number 0 on the right side, because sometimes that throws people off with the notation. It's actually this entire output matrix, which is a 4x4 skew symmetric matrix here. Okay, now, of course, we have the formula for T of ax squared plus bx plus c. It's just this matrix. So if we're setting this equal to this, right, these are being set equal to each other, then of course I can look at the individual slots, right, and make equations out of them, right? So we actually have 16 equations here, because there's 16 entries here and 16 entries here, and they all have to be matched up. So I could figure out, for example, from the top row, that this implies, let's go ahead and write some of this stuff down, that A is equal to 0, and A plus B is equal to 0, and B plus C is equal to 0. And I'm just gonna go dot, dot, dot. There's a whole bunch more equations, but you know what? I already have, just with that much writing, I already have enough information to tell myself that A is 0, B is 0, and C is 0. They're all 0, right? So this actually tells me that A, B, and C, they have to be 0. So if I have a quadratic polynomial that is in the kernel of T, guess what? That polynomial is actually going to be just all coefficients of 0 here, right? And that means that my kernel of T, right? If we want to know which polynomials get mapped over to this all 0 matrix, that is literally going to be 0. It is literally going to be 0. And again, this is not the number 0. This is the vector 0 living in P2 of R. I would accept it like this, but it would be better. It would actually be better to write it as, or it might be helpful to write it at least as 0x squared plus 0x plus 0 to really make it look like a polynomial. One of the big problems on the extra credit quiz that I asked you to do a week and a half or so ago was that I asked people to find the kernel of some transformation, and people were, doing everything correct. They were figuring out what the unknowns were. And I think in the extra credit quiz, there was actually a free variable that showed up. So there was like a T flying around and all this stuff here. So just imagine with me for a second that there was a T there. Okay, I'm gonna make this up. I really want to hit this point. This example does not show what I'm trying to say very well. Let's just pretend for a minute, guys, that when we solved out for A, B, and C, we got T, T, and T. Okay, no need to write it down. I just want to just pretend for a second. So what a lot of people were doing with this when they went on the extra credit quiz is people were then saying, oh, my kernel of T basis is going to be, and then they just wrote down 1, 1, 1, like that. So busting out the variable, which of course we do all the time. The problem is that this 1, 1, 1 looks like a vector in R3. And one thing we know about the kernel of T is that it is a subspace of V. So whatever I'm going to write down for my kernel should look like a vector in V. It should not have 3 slots in it. What it should have instead is it should have, like, I should take this and I should write it as tx squared plus tx plus t, right? Ax squared plus bx plus c as a polynomial. And then I can bust out my t from this and get my basis vector, and it would be that. Okay, again, I'm making all this part up. Does everybody see that? I will be looking for the form of the vectors to be correct. That will be something that's very important. If my vectors in the kernel of T are supposed to look like polynomials, then I want to see polynomials there. Okay, so this would be correct. This one would lose some bit of points for having the wrong notation. So you got to make sure you're writing your vectors in the form of whatever the is. Does that make some sense? It doesn't. This example, it doesn't. It's not very interesting because the kernel is just 0. But if there was something interesting in the kernel like this, just make sure that you do a quick little check. Did I write my vectors in the form of what the vector space V, right, that's what this is, V, should look like? Quadratic polynomials. Yeah. Okay, is that clear to everybody? Just want to really make that point. Okay, great. Well, anyway, so going back to the example we have here, as you can see, the kernel is just 0. So let's go ahead and talk about the range. Yeah, so for the range of T, you remember how to find that? Let's see, range of T. What's our, again, if it was a matrix transformation, the range of T would just be the column space of A. But here, in the more general situation, do you remember how do you find it?
Is it the simplest span that you can make of B?
It's the span, yes,
Yes.
it's the span of, and then we make a list
Yeah.
of the transformed basis vectors of V. What's the nicest basis that you guys know for P2 of R? X squared,
X
X,
and 1.
and 1. I love it. So let's just transform that basis. Now, I should pause again because it doesn't have to be that basis. This is probably the first one everybody thinks. So without any better reason than just to take the easiest example, this would be the basis you would use. But I just wanted to be clear that you can use any basis for T or for V. You don't have to use the standard one. But yeah, I would probably just use this. And then let's just work out what we get out of all of this. So this is going to be the span of, well, it's going to end up being 3 of these 4x4 matrices, right? We're going to have 3 of them here. And we have to write them all out. So T of X squared, right? That's what I'm looking at first. So if I plug in X squared, I also found sometimes people are a little unsure what they're supposed to do here. If I want to know what T of X squared is, keep in mind that this is the formula for T of anything. Anything whatsoever, I can transform it here. So X squared specifically is what we would obtain if the B and the C were 0 and the A was 1. So just for a second, with with this one here, what we're gonna do is we're gonna do A equal to 1, B equal to 0, and C equal to 0. That's gonna give me the x squared as my input. And so then what I do is I look at my matrix, and everywhere I see an A, I put a 1. Everywhere I have a B or a C, I just put a 0. And we just fill in everything we can. So on the first row here, we'll have what? 0, 1, 1, and 0. And on the second row, -1, 0, 0, and 0. And on the third row, -1, 0, 0, and 4. And then on the bottom row, I would have 0, 0, -4, and 0. So there's the first matrix. And guys, again, I'm not in a hurry tonight. If anybody's not clear on how I'm getting this thing worked out, slow me down. I'm happy to go through this very carefully. Okay. Is that okay? So I just put a 1 for the A value, a 0 for B, and a 0 for C to do T of X. The next one would be T of X. And if I want to just pick off the X here, I need to use a 1 for B this time and a 0 for the A and the C. So let's go ahead and write that down for ourselves. A is 0, B is 1, and C is 0. And now I'm going to do the same thing again. I'm just going to go through the matrix, and everywhere I have a B, I'm just going to put a 1. So 0, 0, 1, and 1. Sorry, should be a 1 there. 0, 0, 1, and 1. And then on the second row, 0, 0, 0, and 3. And on the third row, -1, and 0, and 0, and 0. And on the bottom row, again, I'm focusing on where the B's are. -1, -3, 0, and 0. Of course, another self-check on this is that these matrices should be skew symmetric. They should be 4x4 skew symmetric matrices. So you can see that they all are so far. Okay. And then finally for T of 1, I'm going to let A be 0, I'm going to let B be equal to 0, and I'm going to choose C to be 1 this time. And now I go through the matrix one more time. Everywhere I see a C, I replace it with a 1 essentially in that calculation. So the first row is 0, 0, 0, 1. The second row is all zeros. The third row is 0, 0, 0, 1. And on the bottom row, I have a couple of negative C's. So those will be picked up with -1s. -1, 0, -1, and 0. So there you go. And that's also skew symmetric. Okay. So now here's my question for you. What is the basis for the range of T? Bryce? Is that a hand?
Yeah, that should be the basis, using the general range.
Okay, awesome. That's exactly what I was hoping to hear. Guys, we do have to be nervous for a minute about this because these vectors, of course, there's just a list of vectors. They could be LB. In theory, they could be LB. And so I would need a little bit of a reasoning behind why these are actually going to be LI. And as Bryce just said, it comes from the general range already. You guys all know that formula? Oh my goodness, is that a big one, right? That's so important. The dimension of the kernel plus the dimension of the range should add up to the dimension of V. Make sure you put V there. The other day, somebody was putting W there. It's got to be V, right? So it's the dimension of V. Liam?
If the matrices were any smaller, could we have just busted them out? Well, gonna have to be our own, you know? See, like,
No. We're not doing any EROs on these matrices. Definitely not. But we just live with what the outputs of the transformation give us here. That's all. By the way, on the kernel of T, what was the dimension of the kernel here? Got to back up for just a second. Just 0, right? Careful. This is just 0. There's really no basis here. You just have literally the 0 vector by itself. That's a trivial vector space. So this would be a 0 right here, right? Plus whatever this number is has to add up to the dimension of V. What is the dimension of P2 of R right here, V? It's 3, right? Great. So this is a 3. All right, so this is such a nice formula because now if I already did the kernel, then I know what the dimension of the range is. The dimension is 3 according to this equation, just looking at the numbers there. And that tells me that my basis for the range at T should have 3 vectors in it. I don't need to throw anything away, right? Because it's not so obvious to me that these vectors are Li. I can't just glance at it, but they're pretty nasty vectors, to be honest, right? I can't just glance at these and say, oh yeah, they're gonna be Li. Not necessarily, right? They could have been LD. If the kernel had been one-dimensional here, if this kernel had been one-dimensional, then we would have had to say that this is only two-dimensional. And if this was only two-dimensional, then that means this is too many vectors here. And we would need to remove linear dependencies. I know that was something we were more focused on back in chapter 4, which is not really the main thing we're doing for this exam, but that idea would still apply here. You would have to, remember how you do it? You put these vectors into the columns of a matrix.
That's
Oh my God, it would have 16 rows in it.
That's what I was saying.
Yeah, it would be a really nasty matrix. That's why I wouldn't give this to you. But you know, you'd have a huge matrix, you'd have to do your EROs, and then any columns that were unpivoted. This is a good review for the final, right? Any unpivoted columns would correspond to vectors that you have to throw away in order to create your linearly independent set. Yeah, but see, we don't have to do any of that here because the dimension of the range of T is already exactly matching up with how many vectors we were given there. That's pretty nice. That's pretty nice. Okay, so this is actually your basis then. Because it's the right number of vectors. These guys are forming your span for your range of T, so they are a basis, right? So this is the basis for the range of T. All right, awesome. So we've got the kernel and the range done. Now let's just talk about this one-to-one onto both or neither thing really quickly. Well, what do you guys think? Well, first of all, you could have actually started with this question. Before you even think about the kernel and the range explicitly, you could just start with this question because remember that based on V and W, based on these dimensions here, you remember you can always rule out some wrong answers. Let's remember that. I'm gonna write it on the board again. If the dimension of V is less than the dimension of W, this is something I want everybody to know for the exam. Right? If V is smaller than W, then T cannot be onto. Cannot be onto. Remember, onto just means that the range of T equals W. Okay, so if V is smaller than W, it cannot be onto. If the dimension of V is bigger than the dimension of W, in that case, T cannot be one-to-one. One-to-one just means that the kernel is 0. Right, and then the other one is if the V and the W are the same size. So if the dimension of V is equal to the dimension of W, then T is both or neither. Right, so in that case, it would have to be both or neither. So let's just check that out real quick. Let me just make sure this is getting into this video a little bit. So the 3 cases over there, if you just compare the dimension of V with the dimension of W, you can say a lot about this kind of a question right away. What is the dimension of V here? 3, right? This is 3. Okay, and what's the dimension of W? This is I see a 6, I see a 3, I see a 16. And I don't have the right answer yet. Please don't think it. Oh, sorry, I do have the right answer. All right, who said 6? 6. Yeah, it's actually 6. So the reason is that when you write down a 4x4, so if it was just 4x4 matrices, if it said all M4 of R, it would have been 16. But we're not looking at all of the 4x4 matrices. We're only looking at the skew symmetric ones. And a skew symmetric matrix, right, has to have this generic form. So it's going to be something like this, right? Just use these letters, I guess, negative y, negative u, 0, and I'll call this one w. And then negative z, negative v, negative w, and 0. This is the form of a 4x4 skew symmetric matrix. And you guys remember, right, that if I want to find a basis for a vector space, the way I do that, this does go back to chapter 4 a little bit, but what you would do is you write this down, the form of your vector, then you would bust out your variables, right? And you can see that there are 6 variables here that you have to bust out. And so that's going to line up with 6 vectors, right? So your dimension of W is actually 6. Does that make some sense? It's actually 6 here. So V is smaller than W, right? But we're actually up here in this first case. V is smaller than W, then it cannot be onto. So you can cross these off right away. What a lot of people do in my class, from my years of teaching it, is they'll just cross this off with absolutely no explanation whatsoever. So at least do me a little favor so I don't have to question whether I should be giving you full credit or not. And when you cross something off like this, just put a note there to tell me why. The dimension of V is 3, the dimension of W is 6. If I can tell that you've done the dimension analysis to cross those things off, then I can sleep a little better that, okay, that student knows what they're doing. They cross this off because they checked those dimensions. Okay, so the only question then is whether we have a one-to-one transformation or not. And what would be the answer here? It's a yes. We already did the kernel. The kernel was just 0. That means 1-to-1. So the answer here would be that yes, this is 1-to-1. Okay, does that make a little bit of sense? So let's do a quick follow-up on this problem. Let's say that let's say I ask you this follow-up. I guess I'll just call this number 3. So we'll just make it into a new question in and of itself. Let's see if we can figure out for what value of K is there an isomorphism. I did not talk last night about isomorphisms in my review, so I thought maybe tonight I should at least mention this briefly. Is there an isomorphism T going from PK of R over to W? W is the same W as we just did a minute ago, the set of 4x4 skew symmetric matrices. Okay, so this would be, I think there were a couple of homework problems that were kind of along these lines. You know, what would it take to have an isomorphism? Remember, isomorphism is just both 1-to-1 and onto. So you want to have an isomorphism, the very first thing you need to realize is that in order to have both, you have to have the dimensions being the same. So does that tell you what the K value would need to be here? David, what do you think it's going to be? Yeah, it's just going to be 5, and that's because we already know that the dimension of W is 6. So we would need the dimension of V to be 6, right? These would have to have the same dimension if you were going to have an isomorphism. So this would be, so in this case, this would be a transformation. Sorry, the T here is going from P5 of R over to W. Let's say I actually ask you to write the isomorphism down, or an isomorphism down. Suppose I say, hey, I want you to actually give me the isomorphism. So that's where we actually have to create the function. Okay, so once in a while, and there was a handful of homework problems on this where we actually had to create the T. We have to make the inputs and outputs. Think you could do that? You know what the inputs should look like, and you know what the outputs should look like. It's a matter of creating the the function that kind of moves you from inputs to outputs, right? So you would start off with, so this would be the transformation. You'd start off with, I don't know, ax to the fifth plus bx to the fourth plus cx cubed plus bx squared plus ex plus f, right? You take a random input that would look like a P5 of our polynomial, right? Polynomial of degree 5 like this. And then your job would be to then tell me, what are you going to output over here based on this input? And it should be a 4x4 skew symmetric matrix. And you know what you're gonna do? Liam?
You're gonna first start with the zeros on the diagonal,
Okay,
and then you're gonna write A in the first slot, and then B, and then C, and then D, E, and F, and then write the opposites on the bottom.
exactly. So you don't have to get terribly creative with this. You just have to write something that's going to basically work here. That's not going to do it. Let's see what, I'll just
Engineer forgets his
right
alphabet.
here.
Engineer forgets his alphabet.
Yeah, you just gotta put something like that down. And that's all you have to do. This would be a very small amount of writing to do this. If I ask you to write down the isomorphism, you're literally just giving me the formula. And you might be wondering, is this the only correct answer? Definitely not, right? I can sort of scramble up the A through F into any of the 6 positions here, as long as I do the opposites out of the way. So, you know, we got multiple right answers that could be given here, but that would be one of them, for sure. Yeah. Okay, so that's what an isomorphism is. It's just a transformation that is both 1-to-1 and 1-to. Just to kind of refresh your memory about that. We all good on that? Is that clear enough? Okay, let's go to something. So on the review session last night, I think I mentioned I did group work number 14. I think what we have never done though is group work number 15. Just kind of ran out of time this semester. Probably partially because I was gone for a week. I just didn't have time to really get you to do all of these group works. So that's okay. You can use them as practice problems. So let me switch gears and do something off of this group work number 15 here. Is that clock right? Let's see.
No, it's an hour off.
Oh, okay. Gosh, it's only 8:10. Okay. Yeah, I'm really gonna try to stop by 9, because everybody needs to get some sleep. I need to get some office hours, and we need to write an exam. When, yeah, let's say.
And sleep?
And I need to sleep. I might be sleeping during your exam. Okay, well, let's see. So this is gonna be number 4. Okay, so let's try this one. Let's find the general solution. Here we go. So let's do y triple prime plus 3y double prime plus 3y prime plus y equals 2e to the negative x plus 3e to the 2x. This is off of the group work that I just talked about. And let's see what we can do with this one. Yeah, it's, I hear people whispering up at the front. It's really a good idea to just take a minute and pause and ask them, what part of the class does this have anything to do with? Is this linear transformations? No. Is this eigenvalues and eigenvectors? No. Is it a system of differential equations? No, it's none of those things. It's not chapter 6, 7, or 9. It's actually a higher order scalar differential equation. It's what we studied in chapter 8. Okay, so I always like to figure out, I mean, every one of these questions on your test tomorrow is going to be from one of these 4 chapters. And it's just nice to get your head in the right, room or the right box to be thinking about it. So this is coming from chapter 8. And whenever you're asked to do one of these, there's always sort of a three-step process, right? So the three-step process is we first solve the corresponding homogeneous differential equation. That's where we just kind of ignore whatever's on the right side and we just focus on this left side. Okay, so we do that first. Then the second step is to find the particular solution, right? And then the third step is just add them together, right? Just add them together. So let's jump in. This is a good review, just a chance to remember a little bit how this works. For step one, do you guys remember what we need to write down first? Go ahead, Leo.
Associated homogeneous equation.
Yeah, the associated homogeneous equation would just be basically putting a zero over here. So once we've done that, what would be maybe the next thing we'd write down? Nathan? Well, you could rewrite this in the D notation if you wanted to. Now, it's not asking you to do that here. So we could just go straight to the R's. Remember what the name of that equation is? Right, the auxiliary equation. The auxiliary equation, which is just where you turn these derivatives into powers of R. So here I have three derivatives, that becomes R cubed, right? And then the next term we have plus, right, 3R squared, and then plus 3R, and then plus 1. This is the auxiliary equation, and of course we're going to be setting this one equal to 0 right here, okay? So that's the auxiliary equation, and I'm fine with you just writing this down. You can pretty much, anything that you can just look at it and write it down, I'm gonna be okay with that, right? Where I get nervous is when I see stuff that shows up and I'm like, how did they get that? Or I couldn't do that in my head. How are they doing it in their head? Maybe I'm just getting old, but anyway, I think something like this, you could just write it down in your head, it's okay. Now, what you have to do is figure out the values of R here. Okay. If it's a quadratic equation, I would expect everybody to just, if necessary, use the quadratic formula to find the roots. So of course, that's easy enough to do. This one is a cubic equation, and so it's maybe not quite as obvious, but does anybody have a thought about factoring this thing? Yeah.
You do the first two and second two, and
These two?
yeah.
So R squared with R plus 3 like that?
No. Yeah, actually, yeah.
Oh, R squared, R plus 3.
Then you would same thing with this other cycle.
Well, I don't get an R plus 3 out of this though. I see it's R plus 3 here. I actually think in this case, if this had been 3R plus 9, then I could say, okay, I'll factor a 3 and I'll get an R plus 3 out of it. That would have been factoring, like grouping would have worked great, but here, 3R plus 1, I'm not so sure. Anybody else want to try it? Sometimes on my exams, I will have a little thing where you can come, I'll give you the factorization, but I might take off a couple of points like during the test. Because honestly, if you don't get these roots right, you can't do the problem. You really have to get these roots. Liam?
I was thinking R plus 1 cubed.
Well, you got it right. That is exactly right. That is the correct factorization. Now, this one I think is in the realm of I might expect you to be able to do it. I'm obviously not going to give you something really, really hairy because again, if you can't get the roots, then you're not going to be able to show me what you know. So the reason that this works out so nicely actually is because, well, let me give you another tip. You can always test some values of R as possible roots. So when I look at this, it turns out, I don't know if you guys remember this rational roots test from high school algebra, but the roots of a polynomial that are going to be rational. And by the way, you can assume that I would only give you rational roots in this class. Anything that's irrational, that means it's a root that has to be written as an infinite decimal. I'm not going to do that by hand. Right? So any roots that I would give you, any polynomial that I'm going to give you, trust me, it's going to have only rational roots. And the candidates for the rational roots of a polynomial are always just the numbers that divide the constant term. So there are actually only two possible rational roots to this polynomial, and they are 1 and -1. It's always plus or minus. Well, if you plug in 1 for r, you get 8. Doesn't work, right? But if you plug in -1 for r, you get -1 plus 3 minus 3 plus 1, and sure enough, that cancels out to 0. So -1 is a root here. Once you know that -1 is a root, you guys done long division of polynomials before? Everybody doesn't like this. I'll be sure to put on that much. Just kidding. I'm not sure what I'm gonna do. Anyway, so you basically, you do this division here and you say, well, r goes into r cubed, r squared times. And then r squared gets multiplied by r plus 1, and that becomes r cubed plus r squared, and then you subtract. And I get 2r squared plus 3r plus 1, you bring everything down, right? And now you say, well, how many times does r go into 2r squared? The answer is 2r times. And so that 2r then gets multiplied by r plus 1, and we have a 2r squared plus 2r, and again we subtract. We get r plus 1 here. And then how many times does r plus 1 go into r plus 1? Well, that would just be 1 time. And so this becomes your factorization, right? This basically, when you put the r plus 1 here and subtract, you get 0. There's no remainder. Which, by the way, there shouldn't be a remainder because this is going to divide evenly into this thing. So this guy times this guy is equal to this guy. All right, we all know that. If you take 20 and you divide it by 4, you get 5 with a remainder of 0. 5 times 4 is 20. So r squared plus 2r plus 1 times r plus 1 is this thing here. Okay, so, and this one is just a quadratic now. So if you manage to find just one of the 3 roots by happenstance, you just get lucky and you plug in -1 for r and you find that root, then the other 2 roots will not be so hard to figure out because you can get them from factoring the quadratic that's left over in this long division of polynomials here. And the roots of this quadratic are actually 2 more copies of -1. So your roots are, in fact, -1 3 times. And be sure to write down the repeats when they come up. Okay? Yeah, I mean, I don't know if I'm gonna, I think there was one homework problem where you actually had to do this long division as well. We haven't done a lot of it, but technically I could do this, I guess. I don't know, we'll see. Anyhow, so we get these roots, and so now I write down the from that I can write down the complementary function right away. Yeah. What do we do for the repeats in this situation? See?
You stack the x's.
This is where the x stacking comes in, right? So exactly. So from here, I'm going to write down the complementary function. Does anybody want to take on the first term for me? C1
e to the -1, -x.
Right, -1 times x. So C1 e to the -x. Can I get somebody else to help me with the second term? Eduardo?
Is it c2 x e to the -x?
Nice. Stack an x there. Looks good. And can I get a third volunteer, Tony?
c3 x squared.
Nice. Yes, that looks perfect. I'm going to go ahead and put a box around that so I can easily find it. So that's step 1, and that took a little bit of work just because getting the roots was maybe a little harder than normal. Okay, but that would be. Okay, so now we're going to start thinking about step 2, unless there's a question here so far. So step 2, let's see. Step 2 is where we have to find one particular solution. Can somebody remind me what are the methods that we have for finding the particular solution in step 2? We have annihilators and one more time? The variation of parameters, right? You should not expect the exam to tell you which way to do it, right? And I'm probably going to set up the problem so that only one of the ways is going to work. So you're going to have to know, how do you decide whether you're going to use annihilators or variation of parameters? Can anybody tell me sort of the scenarios that allow me for either of those methods, Nathan? Oh, yeah, let's stop right there. For variation of parameters, we only learned it for second order. So I would not ask you something of third order that you were supposed to do with variation of parameters. Okay, so that's a really good point. What are the constraints on the annihilator method? Okay, we have a table of annihilators here. So this is what I'm going to give you on the exam, right? There's, a list here, the things that we know how to annihilate. What are they? Powers of x, sines and cosines, e to the ax, and then combinations of those. So I want to look at my f of x here and ask myself, do I even know how to annihilate this, right? And it turns out we do, right? We do. This is good because we have just exponentials, right? The factors of 2 and 3 in the front of these terms does not make us flinch at all, right? We just don't even worry about the 2 and the 3. What I'm going to do here, I'm going to go ahead right here. I'll start step 2. What I have to do you remember if I've got two things added together over here on the right side, do I just add those annihilators? Actually multiply them. Good remembering on that. Yeah, so we have to actually take the individual annihilators and multiply them. So what is the annihilator of e to the negative x? Jesse?
A D.
Right, that's going to be a d plus 1. Okay, and then what about the annihilator of e to the 2x?
Minus 2.
D minus 2, exactly. So we get those two annihilators for these two terms, and even though this is a plus right here in between those two terms, when we're doing the annihilators that correspond to that, we end up multiplying, okay? And again, just to make it very clear, the 2 and the 3 that are in front here, they don't affect anything. We can kind of just ignore those. They're not going to change the annihilators at all. Okay, so in step 2, we're going to get some new roots. Let me just remind you, I like to call the roots in step 1. When you watched my video about this, I think I tried to refer to these as the old roots. These are the roots that we get in the initial part of the problem. And now from here, we're going to get some new roots. And I don't mind if you just kind of jump straight into it here. The D's are going to turn into R's again. We're going to set the product equal to 0 again. And the new roots are going to be -1 and 2. Again, be sure to write down repeats when they happen. But in this case, one of the new roots is actually a repeat of some of the old roots. So the point about that is that the x stacking has to continue, right? We just continue with the x stacking. So the particular solution here, this is for step 2, right? The form of this particular solution is there's going to be 2 parts to it, right? The first part is going to have, I'm going to put an A here. The -1 root is now showing up for the 4th time, right? We had 3 repeats already, and now this is the 4th time. I can go back to the complementary function and look at what was the last power of x that was stacked here. And I can just jack that up by 1 and just continue along my way here. So it would be 3 powers of x times e to the -x, right? And then there will be another term for the other root that is new. This root is just 2. So that's just going to be b e to the 2x. Okay. And there is the form. What I've put in this box here, this is the form. It's what I call the form of the particular solution. Now, sometimes I will only ask you for that. You really need to read the question carefully. If the question just says, write down the form of the particular solution, it's basically game over right here. You have the particular solution, you have the complementary function, and of course, step 3 is where you just add them together. So you're pretty much done in that case. But if the question just says, find the general solution and there's no reference to any shortcuts on the particular solution, then you really do need to solve for A and B. Now, I'm gonna give you a little pro tip about this though. The pro tip here for all of you test takers out there is going to be that solving for A and B is not going to be worth a whole huge amount of points, right? Maybe this whole problem is worth, let's just be generous and say 10 points or something like that, just to make a nice round number. If you did all of step 1 correctly, you put this form down correctly, and then you summarized step 3 correctly, but you didn't do the A and the B, you're probably going to lose maybe 2 or 3 points. You're not going to lose much credit at all. The reason I'm telling you that is if you're running out of time on the exam, let's just say that you just didn't manage your time very well and you're running out of time, I would not lose a huge amount of sleep over solving for the A and the B. It takes a fair bit of work. Because guys, I have to take 3 derivatives of that right now. And I can already see that I'm gonna have to use the product rule, and oh my goodness, I'm gonna have to do it 3 times. It's gonna be kind of a mess. So it will take some effort to get, I mean, I'm gonna try to write questions where this is not too hideous, right? This isn't my goal in Math 250B to just see who I can wither out with taking derivatives here. That's not what I'm trying to do. But I might give you something where you have to do a little bit of work to solve for the constants. This one's pretty, I don't know why it came up. This is off of the group work, so I must have thought it was okay. But you can see that I'm gonna have to take 3 derivatives of this, right? I think I'm gonna let you read the solutions. I think instead of doing it, because this is, I mean, this will take, I'll just show you the first derivative, you have to take the product rule here. So you'd have the A in front, and then you take, the derivative of the first one times the second one, plus the first one times the derivative of the second one, which is gonna be something like that. Right? The B part isn't so bad because you just keep pulling down factors of 2 each time. Right, so this would be the first derivative. I'm not even close to done. I have to take 2 more derivatives. And then after I get all of the derivatives, keep in mind, then you have to pile it all together with the left-hand side. You have to plug everything in. 3 derivatives plus 3 times 2 derivatives plus 3 times 1 derivative plus the original. And all that has to get added up and set equal to this. Right. So it's kind of a pain. I don't know what I did in my, I wonder if this is the one. I'm just curious in my solutions to the group work. I'm gonna just look this up really quick. I think I probably just wrote down, oh, here's the process, and I probably didn't actually show it. I just want to look. I'm sorry. Give me a second. I just want to see what did I do with this crazy problem. I should probably just change this one. What did I write here? Oh. The form of the trial solution is that, okay, good. Substituting this into the differential equation and equating coefficients of the right-hand side, we can solve for A and B. I didn't do it. Okay, guys, if I'm too lazy to do it and if I'm punting on something like that, it probably means I'm not going to ask you to do it. So I wouldn't worry about this one too much. When would I ask you to do it to solve for A and B? First of all, it would be a low order differential equation, so you don't have to take too many derivatives. 3 might be okay, 2 or 3. And also the form of the particular solution would probably be, it would be set up by me on purpose to be easy to take derivatives of. Like if the first part wasn't here and your form was just that, well, that wouldn't be so bad. Anybody can take 3 derivatives of this pretty quickly and then just plug everything in. So anyway, I'm not going to do this one right now. Don't forget to write down step 3 though. Step 3 is where you then summarize your answer, y of x. Remember, this is going to consist of, and this will be worth a point or 2 just to write this down. So, if you're one of the people that likes to just get every little bit of partial credit point by point, this is something that would be worth writing down, just to remind me that you know how to wrap everything up at the end. Okay, so that's step 3. You don't need to recopy what these things are, as long as I can find your complementary function and your particular solution, like putting them in boxes is great, then I can just immediately see that you know how to wrap things up from there. So that looks pretty good. Okie dokie. Look okay, guys? Let's do something else then. Last night, by the way, I did a variation of parameters problem. If you need a refresher on that, maybe you could watch that video. I wasn't gonna do one tonight. Just make sure on variation of parameters that you know the formulas for the U1 and the U2. So I'll just write them here just to get them in your head right now. When you're solving for the particular solution using variation of parameters, this is what you have to do. Okay, so, and then the particular solution in this case, this is just a quick review. It's just U1 times Y1 plus U2 times Y2. Right? So make sure you can find the Wronski in here, that's what W is. And then the Y1 and the Y2. Nathan?
You did say last night, I just want to make sure that the Y1, the Y2, the order of them doesn't particularly matter.
Correct. When you're doing the Y1 and the Y2 in step 1,
Okay.
which term comes first and which term comes second can be.
And so then if I like put my Y1, like was your.
I would still, you would still want to have the notation set up with these equations like this.
But my Y1 could technically be like someone else's one. So
Correct.
That's fine.
Yeah, that's totally okay. Totally okay. You'll get the same right answer either.
For W, you would be doing the Wronski, you know, saying this, if this was a variation of time.
Yeah.
It would be 2e to the negative x plus 3e. That's.
No, the Wronskian, okay, first of all, there would only be 2 solutions here. These would be your Y1 and your Y2. And you wouldn't have a third one because it would only be a second order equation. So your Wronskian would be, you know, the way this works is it's the determinant of, and then you put Y1 and Y2 here, and the derivatives of those go here. And it's a 2 by 2 matrix in this case. Yeah, Jessica.
What does the F represent?
Oh, the F is given, it's whatever's on the right-hand side of the original problem. So the differential equation is of this generic form. The capital F is just whatever was given on the right-hand side of the problem.
Yeah, the 2e to the negative x.
Yeah, it'd be the 2e to the negative x plus 3e to the 2x on the right-hand side here. Yeah, definitely. Yeah, sometimes people will, you know, they'll forget the minus sign or they'll do something a little screwy here. You know, obviously you won't get full credit if you got a little mistake like that, but it won't be a fatal error. Fatal errors are things like trying to use annihilators when you're supposed to be doing variation of parameters. Don't make that mistake. Or using variation of parameters when you're supposed to be using annihilators. So really think carefully which tool is supposed to be used on a given problem. If it's a higher than second order equation, and if you know how to annihilate your function, you should use annihilators for sure. Okay, more than likely, I'm not going to tell you which method to use. Right, okay. I think what I'd like to do, spend another 25 minutes or so, we'll call it a night. I'd like to do a little bit of theoretical stuff with eigenvalues again. I did some last night, but I will probably have something along those lines for you to do. So let's do this example. This is number 5. Let's do this. Let's suppose that A is diagonalizable with, and A is going to be n by n, sorry. So A is an n by n diagonalizable matrix with eigenvalues lambda 1, lambda 2, and dot, 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 up to lambda n. And here's what I'd like to do. I'm going to do a little proof here. Prove that the determinant of A is the product of those lambdas. Now, in case that kind of looks familiar to you, that's actually one of the fun facts. So the fun facts are that if you add up the lambdas, you should get the trace of your matrix. And if you multiply your lambdas, you should get the determinant of your matrix. So I actually think we can prove this. Now, I wasn't gonna ask it, except I looked back at one of my old exams for this class and actually had it on there. So I must have thought this was reasonable. So let's see if we can think about it. When we have a diagonalizable matrix, this just means, again, it's just another word for non-defective. What can we do? Like, do we have any, what's our theory in the case of a diagonalizable matrix? Do we have any equations that we learned that might be helpful? Yeah, go ahead.
S inverse AS equals D.
Yeah, that's exactly what I was thinking about. So in a diagonalizable matrix, that's a great starting point. Let's just recall that we have, in this case, we have S inverse AS is equal to D. Let's just remember what the S and the D are. So just to remind you here, the D is just the diagonal matrix that has the lambdas going down the diagonal. So lambda 1, lambda 2, and dot, dot, dot up to lambda n. That's just a diagonal matrix with the eigenvalues on the diagonal. And if you remember also, this is one that you guys watched a video on. So that's why I'm wanting to review it briefly here. The S matrix is the one where you put the vectors, the eigenvectors, into the columns of the matrix. So I'm just going to draw bars to separate those columns out like so. So that would be the S that you would have right there. Okay. And remember, if the matrix is diagonalizable, then these eigenvectors are all Li, right? They are all linearly independent. And this is actually an invertible matrix because its columns are Li. And that's why we can write S inverse down, and it makes sense, right? It's reasonable to do that. Okay, so, and by the way, guys, last night in the review session, I did an example where I gave people a matrix and I said, write down the S, write down the D. We should be able to do these things, right? So I wasn't going to do an actual computational one of those tonight unless somebody requests it. But that's definitely fair game for your exam, is to, I give you a matrix. Well, it's like the extra credit quiz. I give you a matrix and I say, is it diagonalizable? If it is, find S and find D, right? So that's certainly something worth reviewing if it's a little rusty for you. But anyway, this is kind of just the setup of how the whole thing works. I would memorize this equation better than having to rederive it. Okay, I did, of course, derive it for you when we covered this section, but it's just nice to have it memorized. Does anybody have, let's get back to what we're actually being asked to do here. Does anybody have any thoughts about how I'm going to be able to prove that the determinant of A is the product of the lambdas based on anything new that we've now put down in the solution so far? Do we know what the determinant of D is? Eduardo?
Isn't it just like a fun fact where you can just multiply the diagonal?
Yeah, that's actually even before the fun facts. If you remember way back in the chapter on determinants, we said that if a matrix is triangular, it's upper triangular or lower triangular, and that includes being diagonal. If the matrix is a diagonal matrix or a triangular matrix, the determinant of that matrix is just the product of the lambdas of the main diagonal, which in this case is just the lambdas that we want. So actually, we know that the determinant of D is lambda 1 times lambda 2 times lambda 3 and so on. How does that translate with the determinant of A? Because they're asking us to show that the determinant of A is the same thing as the determinant of D. Does that seem reasonable? Actually really like this problem. Um, you know, I can take this equation here and just take the determinant of both sides. Right? So what we have is that the determinant of S inverse AS should agree with the determinant of D. If I just literally take the determinant of both sides, then I'm good. Maybe you didn't get this far. First of all, by the way, this would only be worth 4 or 5 points. I generally don't make these theoretical problems worth huge amounts of points. And I probably also would give you a choice, probably like, you know, I don't know, do 3 out of these 4 or something like that. Give you a freebie to just ignore. But if you just wrote down this basic background material for it, I'd already be giving you at least half the credit. Okay, so it would be, at this point, you'd be trying to fight for a couple extra points, basically, to get the rest of this. But the idea is, if you take the determinant of both sides, because we know what the determinant of D is, it is actually exactly what we want. It's all of these lambdas multiplied together. That's on the right-hand side. Because D is just this diagonal matrix, yeah? So the determinant of a diagonal matrix is literally just whatever the product of the diagonal numbers is. So that's easy enough to handle that part. And then now we actually have something that really does technically belong with the first part of the semester, which is, do you remember some properties of determinants? You have the determinant of A times B. There was a property that said, oh, well, you can break that up. It's just the determinant of A times the determinant of B. On the left side here, guys, we can do that. We can say, look, this is just the determinant of S inverse times the determinant of A times the determinant of S. You can literally just chop that into 3 terms, into 3 separate determinants like so. And that should be pretty nice, right? And then does anybody remember what the formula was for the determinant of the inverse of a matrix? I know this is from chapter 3 and the test is not supposed to cover chapter 3 right now. So in that sense, it's not a great thing for me to be asking you, but guys, we have a final a week from now. So we may as well remember what it is. The formula for the determinant of the inverse of a matrix, it's just 1 over the determinant of the original matrix, right? So this determinant of S inverse is just 1 over the determinant of S, right? And then we still have determinant of A here. We still have the determinant of S here. And the right-hand side, I'm pretty happy with that. I'm just going to recopy it again, same thing, right? And you see where I'm going with this? See where it's going to go from here? What am I going to do? Eduardo?
Would the 1 over determinant of S cancel out with the determinant of S?
Absolutely. These are just numbers, guys. The determinant is just a number. So you have a number and it's reciprocal. They're just being multiplied there on the left side. Just cancel them. And now you're good to go, right? You have determinant of A is the only thing left over here, equals the product of those lambdas. So that's actually how it works. Okay, so I like the problem because it does review diagonalization, sort of the theory of that. And it proves one of our fun facts that we have been using quite regularly already. So it's just nice to kind of see how that works out. What do you guys think? Does that seem okay? Again, I don't want you freaking out. Like this would be like a 5-point problem. If you even just wrote down any part of this to get started, I'd probably give you about half the credit for it. You're not going to bomb the exam based on something like this. Okay, be nice to get it right. Okay, but you know, try not to feel like you're being expected to like totally pull these things out. I understand it's not that simple. Let's do one more that's also kind of a theoretical problem, and this one will be more similar to one that I did last night, but it was such a important type of problem that I think I want to do it again tonight as well. Unless there's a question here. Everybody okay? Again, don't sit there wondering, oh gee, I don't know if I could have come up with that. What I really care about is, do you understand it now? If there's still holes in your thinking here, let's stop and talk about it a little bit.
I
Nathan?
guess, why do we know that the determinant of S inverse AS has to equal the determinant of P? Just because they equal each other?
If two matrices are equal, then their determinants are equal.
Okay.
Yeah, that's exactly where that goes, yeah. Absolutely. Anything else for the moment? Again, this is the theoretical side of it. Make sure you can do the practical side of it too. So if I actually give you a 3x3 matrix and I say, is it diagonalizable, and find S and D and all that good stuff, like what was on the extra credit quiz, make sure you can do that. In fact, one thing I might recommend also, I know some of you are probably still thinking about doing a sample midterm. Very good idea to do that if you haven't already. If you've already kind of done that and you're like, oh, I don't know what I'm going to review between now and tomorrow. If you haven't gone back and tried that extra credit quiz again, not a bad idea. I put a blank copy of it in the resources folder, but click that thing open, just see if you can get 100% on it this time. Okay, because I don't think there might have been one person that got it all right first time, but it wasn't too solid overall. So that'd be a good thing to look at again. And one of the problems on it is this, on that extra credit quiz. So if you want to look for a chance to practice that again, that'd be a good place to do it. Very, very likely to have this on the test because this is, I mean, diagonalization is huge. Now, one of the main applications of it was Markov processes. Do you remember on one of those videos where there were the students switching between the two professors' classes? Like 20% of the students went from Professor A to Professor B, and then 10% went from B back to A each day, and this just goes on. It's kind of like one of these oscillating problems, and the question is, oh, how do the students end up distributed by the end of the semester when t goes to infinity? That I'm not going to put on this test because we didn't do any homework on it, and it was just for you to be exposed to why this might be a useful thing in the real world. Because you have to know, well, why do we care about, well, who cares if we could diagonalize the matrix? Like, what's that good for? So I wanted you to see a real serious application of it. But I won't ask you about Markov processes on the test. We did not do enough with that for me to feel like that would be reasonable. But just know that that's there, and it's something that gives this purpose. And make sure you can do this process. Write down S, write down D, know this equation, and you should be good. The one I did last night actually had complex numbers in it as well. So it was kind of a twist. It was an extra twist because you had to deal with complex numbers in the S and in the D. And that can certainly happen as well. Okay, without any further ado, let me do one more theoretical problem here and about eigenvalues. So let's suppose that A is n by n. Let's do A cubed plus 5A squared plus 8 times the identity matrix equals the zero matrix. So I'm just going to imagine, I'm making this up, by the way, just totally making it up. And then let's assume that lambda is an eigenvalue of A. Okay, so you have an eigenvalue for this matrix. And then here's what I would like us to prove. Again, this would be like a 5-point problem. It would not be a make or break for anybody's exam. But what I would ask you to prove is that lambda cubed plus 5 lambda squared plus 8 is equal to 0. So if a matrix satisfies some equation, some polynomial type of equation, then any one of its eigenvalues actually has to satisfy, basically it's the same equation, right? On the level of numbers. This is a matrix equation. This is an equation involving numbers, and the eigenvalues have to satisfy the same equation that the original matrix did. It's kind of a neat fact. And I'm literally just making up the equation there. The A cubed plus 5A squared plus 8I. Last night I used a different one, but it's the same idea. It's the same idea. So let's see how we would do this problem. Okay, this is a good little exercise as well. So we have an eigenvalue of A. Are there any equations or any bells going off in anybody's mind right now about anything? Taylor?
A vector is equal to lambda vector.
Okay, guys, the most important equation in chapter 7, we're not gonna get out of here without bringing that up, right? I talk about it all the time. AV equals lambda V, right? And if you just write that down, I'm probably already gonna be giving you a good, nice chunk of partial credit just for knowing this equation. I'll point out here that the eigenvector V should not be 0. So just to remind you again, eigenvectors are not supposed to be 0. And that actually does turn out to be important in this work. So AV equals lambda V, right? For as many times as I keep harping on it, I keep saying how important the equation is, you'd be surprised how many times, at least in the past when I've taught the class, I have a hard time getting people to learn it correctly. I'll see things like A lambda equals V lambda, stuff like that, which this doesn't make any sense. Doesn't even make any sense. Or I'll see things like A equals lambda. That doesn't make any sense. Matrix is never equal to a number. Or I'll see AV equals lambda. And there's no V on the right hand side. I'm just writing down every single thing over here is just totally nonsense. Doesn't even make any sense. You have a matrix equal to a vector. Here you have a matrix equal to a number. Here you have a vector equal to a number, right? They aren't even living in the same universes. I couldn't even begin to make sense of it. So really be careful. If you have to put this under your pillow tonight, and like say it 10 times before you go to sleep or something, fine. Whatever it takes to get this right, there's a pretty good chance that this might come in handy tomorrow. Okay, so that's what we have. And that's a good starting point. Does anybody have a thought on how we can now use that to help ourselves with this problem? We see that there are powers of A that are going to be required here, right? I see an A squared and an A cubed. So here's another question for you. Would this be okay? Cube both sides? Great, everybody's saying no. This would not make sense either. Why not? That's because you're cubing a vector. And I'm like, what does that mean? If I give you the vector 1, 2, 3, and I say I want you to cube the vector, it doesn't even make any sense. We don't know how to multiply vectors by themselves, right? What do we know how to do? We know how to add vectors. We know how to scalar multiply vectors. Those are the vector space operations. We don't talk about squaring a vector or cubing a vector, right? So this would not be the way to bring the A cubed into the solution. I do want to get A cubed into it because I see it in the question over there, but this is not the way to do it, okay? So let's go back again. Does anybody have an idea how we could bring the A cubed into sort of the picture here? We don't have it on our solution at all so far. Taylor?
Times both sides by A squared.
Okay, what if we just apply the A on both sides? So like, for example, I could take A of AV equals A of lambda V, and then I could do it again. I could do A of V equals A lambda V. Now I'm doing something totally legal, which is I'm just multiplying by A on both sides of the equal sign. This is legitimate. This is totally good. Right? So what I have here is A cubed V on the left side, right? So let's just see. So let's actually just write that down. A cubed V. And so what is it equal to? Well, we wrote it right here. I'm going to write this down as A squared times lambda V. Okay. Let's not even worry about what we're trying to prove yet. Let's just kind of play with this for a minute. This lambda is just a number. I don't mind pulling numbers out into the front. Let's just pull that one lambda out in front and just get a squared v here. Now, a squared v, well, that's just a v, right? And I see the AV again. Change that AV back to lambda v. Okay, so we just do that again. Lambda times A times lambda v. Pull all of the lambdas out to the front. We get lambda squared AV. And one more time, the AV changes into lambda v, and we get lambda cubed of v. So guys, here is what we were really hoping to get to. A cubed v is equal to lambda cubed v. Right. I did not get that by cubing both sides. I got that by applying the A on both sides, on the left of both sides, and then simplifying it. Okay, so we have, let's just summarize what we have there. We have A cubed V equals lambda cubed V. That's a sensible statement. And if we wanted to, we might as well write it down. We could have stopped with just A squared V, and that would have been equal to lambda squared V. So we could take any power of A times V, and it would be equal to that same power of lambda times V. Okay, so we are getting some of the key points out of the way here that we're going to need. And I don't think I need a whole lot more room, just this much here. We should be able to wrap up the argument now. Okay, so let me come over here and see if we can finish this off. Guys, this equation, now we're going to look at what we have here. This equation, this is just a matrix on the left and a matrix on the right. We can apply both of those matrices to the same V that we've been playing with here on both sides. So we have, this is the way you're going to do this. We're going to take A cubed plus 5A squared plus 8 times the identity of V, and it should be equal to the zero matrix of V. What did I do here? I just literally took what was circled over there and just put the vector V on both sides of it. So this matrix applied to V should equal 0 applied to V. That's what it is. What happens when I take a matrix of all zeros and multiply it by a vector? What's going to happen? All zeros, and I multiply by, I don't know, ABC.
Zero.
Just zeros it all out, doesn't it? This just becomes 0 on the right-hand side. For sure. On the right-hand side, that's just going to be 0. And then what about on the left-hand side? Well, on the left-hand side, I can just distribute this out now. I have A cubed V plus 5A squared V plus 8V. Notice I dropped the identity matrix only because it's like multiplying by 1, as we've learned earlier. So that's my left-hand side. And does anybody see any algebra that I might, well, actually, I don't need to do any algebra. I already wrote it down, didn't I? A cubed V can be changed to lambda cubed V, right? So on the left here, this is lambda cubed V. And then plus 5 times A squared V is just lambda squared V. And then we'll just recopy the 8V here. We're just about done. Just about got it. And what's the algebra that you would be thinking about doing right here? Anything?
Factor it out.
Right, there's a V in every one of these terms now. Let's just factor it out over here, right? Just factor it out and see what we got. What do we have on the left? I've got lambda cubed plus 5 lambda squared plus 8. Just factor that V right out of the right-hand side. And now I have two things multiplied together equaling 0. But the V was not 0. So you have a vector that's not 0, and now you have scalar multiplied it by this number, and it's become 0. So what's that tell you about that number? It is 0, right? This part in the parentheses has to be 0 because otherwise, if it wasn't 0 and v wasn't 0, you wouldn't have gotten 0 when you multiplied them together. So that's what you were trying to prove. I gave you guys the bonus version of this problem. I think last night it was only a squared equation. I didn't go all the way up to 8. This one's a little bit problem. Doesn't
On the midterm, do you want us to like read through that part, like the whole a squared equals m squared? Or should we just do?
this thing here?
Yeah,
I think you probably would want to write that down. Yeah, I mean, I could certainly give you some points for doing that. I think that would be better than just like assuming it. Yeah. But you would get partial credit for sure just for even writing this down. If you didn't write anything else down, you wrote this down, I'd be giving you close to half the points probably. Because I've been making such a big deal about this. It's really the most important equation in chapter 7. So, other questions on this? Well, it's not 10 o'clock, but it almost feels like 10 o'clock to me. I don't know. I think I'm going to stop with throwing problems at you. At some point, I have to stop talking and let you guys sort of soak up what you need to soak up. We covered some good ground tonight. I didn't do a lot with the variation of parameters. We didn't actually do an example of that. I didn't do anything with phase portraits. So, if you need to refresh your memory about it, that's not too difficult. It's just, okay, you got to look at the eigenvalues of a 2x2 matrix, spirals and circles and saddles and sinks and sources, right? So that's something that's maybe worth just a few minutes. It's not going to be a big thing on the test, but there could be a phase portrait somewhere. I didn't do the Floy thing. There wasn't a whole lot with complex numbers on tonight's review. If you go back to yesterday's video, you'll find some examples with that in it. You should be able to do the Floy method. Remember, that would be for a non-defective matrix that has complex eigenvalue, eigenvector pairs. So I did not do one of those here. We did have it recently in the homework. What else? Were there other topics that I didn't really do too good with? I feel pretty decent with it overall. You know, I think it's up to you sort of where you need to focus your time, what you need to spend your time on. I would recommend if you haven't looked at either sample midterm, that before you come in to take the test tomorrow, you at least try one of them. But you know, there's a lot of stuff in that resources folder. Don't feel like you have to do all that stuff. Okay, you've come to this review, which is huge. You've got a sample midterm maybe to play with. And of course, I'm gonna have office hours the rest of tonight, and if anybody wants to hang out and do anything else, ask me any specific questions to go over. But I think this is pretty decent. I feel like I feel pretty good about what we've talked about so far. So does that sound okay to everybody? Kind of put a period here and call it a night. Well, I'm not gonna call it a night. I mean, I'm just go down to my office and continue burning the midnight oil. But if any of you want to go home or get some rest, that's probably not a bad thought either. I will be sending out